Hello and welcome to week 2 of Science 137 at American Military University. Glad you're back. Those of you on active duty, thank you for your continued service. And we'll jump into the content from week 2, which is all about how the Earth is heated from a planetary point of view. It's about energy transfer and heating and taking temperature, and we even get into the reasons why we have seasons when we do. So some of the first content from this week is the concepts of how energy is transferred, how things are heated. There are 3 ways that heating energy can be transferred from one location to another. The first is conduction, and that's through a medium. Literally, you heat one part of something, and that transfers the heat to another part of something. We see this in the book. The example is the same example that they use in every book, and that's holding the pen over the flame. But the concept there is that the pen itself, the metal, is a good conductor, so it can rapidly transfer the energy from the part of the pen that's over the flame to the part of the pen that's between your fingers. So then a good classic example. So conduction happens when energy flows through an object or a medium or material. Some materials are good conductors of heat, which means the heat flows rapidly through that. Metals are good conductors of heat. Some materials are very poor conductors of heat, like wood. You do the same experiment with a stick of wood, and even though the flaming end would just burst into flames, the part that you would hold would pretty much stay the same temperature, because wood's a very poor conductor of heat. Energy or heat doesn't travel through the medium that rapidly. Air, it turns out, is also a very poor conductor of heat. Another mechanism is convection, and that's how a lot of fluids will transfer heat, and that is literally the bubbling up of fluid to where a warm piece moves to a colder area, and that's how heat is distributed by convection within a fluid. You can do this at home. You can see convection at work by heating up a pan of water on the stove, and even long before the water boils, you'll start to notice motion within that fluid, and that is because near the bottom of the pan where the heating is occurring, that water is heated. It becomes less dense, it becomes buoyant, starts to move around within the fluid, and that is one way that the heating that you're applying just to the bottom of that water around the edges of the pan is distributed eventually throughout the fluid. So that's convection. The third is radiation, which is important to us because that's how the sun transmits its energy to us, and radiation has to do with the transmission of electromagnetic waves across space from one object to another. And it is some of the concepts. We won't be in this class responsible for the math, but we'll go over. One thing to know is the order of the wavelengths based on the type of energy, especially ultraviolet, slightly higher energy, higher frequency, shorter wavelengths, through the visible light, and then to infrared light, which has, relative to those two, lower frequency, longer wavelengths. We'll come back to the concept of wavelengths, and the chapter gets into the concept of absorption and re-emission and a lot of greenhouse effect stuff. We won't worry about the physics of that until week 15 with climate change. We'll touch on it a little bit then. But one takeaway point from that section is even without all of the climate change and greenhouse gases stuff, the natural atmosphere itself does have a natural greenhouse effect that keeps the surface of the Earth warmer than it would be without an atmosphere. He explains the physics of how that happens if you're interested in it. It's a good read. Basically, the atmosphere is fairly transparent to the incoming energy, but at the wavelengths that the Earth gives off into space, certain atmospheric gases can trap some of that outgoing energy, re-emit it back to the surface, keep the surface a little warmer than it would be without an atmosphere. Again, we won't, at least in this part of the course, go too deeply into that, but it is a friendly read if you'd like that. Finally, another point that's made in the chapter, and it's a critical point in in this semester, is the atmosphere is actually heated from below. The vast majority of the heating in the atmosphere occurs at the bottom of the atmosphere. When the sun comes in, strikes the surface of the planet, its energy strikes the surface of the planet, heats the surface of the Earth up, and that is transmitted into the lower part of the atmosphere, and the atmosphere is heated from below. The warmest part of the atmosphere, or at least the parts that we'll talk about in this course, are nearest the surface. Again, the atmosphere is heated from below in the part of the atmosphere where weather happens. The warmest, in general, on average, part of the atmosphere is near the surface, and it's going to cool as you go up. So that's what my cat is doing over there. So that's that. Talk about energy balance, and then we get into why the Earth has seasons, and it may come as a surprise to you. It certainly did to me when I took my first meteorology course, that the Earth is actually closest to the Sun sometime in January. So it's January of 2012. We probably just passed that point in our orbit where the Earth is actually closest to the Sun. But here in the Northern Hemisphere, where almost all of us are, I think all of us are, this is one of the coldest times of the year. And the end of the chapter goes into the reasons for that, and it has very little to do with how far away from the Sun we are, and almost everything to do with the fact that our planet is tilted with respect to the Sun. Whereas we go around the Sun in the summertime, the North Pole and the Northern Hemisphere is tilted towards the Sun, and we get more direct rays in the Northern Hemisphere and longer days, and so we typically heat up during that season. As we continue around the Sun, we get in January to a point where, even though we're a little closer to the Sun, the northern part of the Earth is tilted away from the Sun, which means shorter days and much less direct sunlight for most of us, and that leads to our cold season. So be sure that you're comfortable with the kind of whole concept of why we have the seasons and when is the equinox and all of that, because that will definitely be quizzed in the not too distant future. So again, the reason we have summer and winter and transition between those two has very, very little to do with how far we are from the Sun in our orbit, and has almost everything to do with the fact that our North Pole is basically pointing at the North Star the entire time around the Sun. Finally, we have a map assignment this week, and that map assignment, we're going to build on that throughout the semester. So we'll have 5 more map assignments that use data from the same day, the same snapshot, to kind of determine what's going on with the weather. So this week's version is just about understanding the wind plots on there. So if you look at the map assignment, it's a map of Oklahoma with about 100 wind observations. They look like little feathery sticks across the state. And what we're going to do right now is go through with this this high-tech piece of equipment here and just build a single wind observation, and hopefully the logic of what goes into building that wind observation, you can take that with you to the map assignment and say, okay, there's 100 of these on there. I think I do know what's going on with the wind at each one of those stations. And so this is part of the symbology, or the symbols that weather people, meteorologists, and anyone interested in observing and recording and interpreting weather maps will use. And you'll see this quite a bit. If you catch the weather bug and you continue to look into meteorology, you will no doubt be looking at maps with these so-called station models on them. Station on a map, you can have the temperature, you can have the relative humidity, the dew point, whatever, and you'll almost always have wind on there. So this is how the wind works. So we're interested in the wind at this station, this little bitty X right here, and we're going to depict the wind at this station on a map. Up is to the north, down is to the south, left is west, and right is to the east. And so for starters, for this station, I'm going to draw a line sticking off to the southwest. So wind has two components. The first component is the direction. The second component is the speed. And what we draw here in blue is going to describe both the speed and the direction. So the fact that this stick is sticking off to the southwest indicates a southwesterly wind, or winds are blowing from the southwest. So this stick points into the wind from the station. So this is called a southwesterly wind. We'll go over this. We'll finish the station model, and then we'll go over all the logic. And let's say this wind is blowing 25 miles per hour, and we would show that just like so at this station. So again, here's the station location. This is where the wind is occurring, and we have 25 mile an hour wind, and that is 10 miles an hour for the first long barb, 10 miles an hour for the second long barb, and 5 miles an hour for the little short barb. So you add those together, 10 plus 5 means approximately 25 mile per hour wind from the southwest blowing to the station. It's a southwesterly wind, and that's important. When you describe the wind direction, and we'll go over this in the map assignments, I think even in one of the quizzes, a northerly wind is from the north. A southerly wind is from the south. A southwesterly wind is from the southwest. It's just like if you're a northern person, you're from the north. If you're a northerly wind, you're from the north. So again, wind direction indicates the origin of the wind. Where is the wind coming from? Okay, and so this is again a 10, 20, 25 mile per hour wind blowing from the southwest at this station. So it's pretty counterintuitive on why would they have this be blowing into the wind. It seems like it would blow the other way. Well, the way they used to do it when they had a little more room on the maps, a little fewer stations, is they would actually, and this would be a solid line, they would have actually drawn that line all the way through the station, and we would see an arrow shooting through the station, and the feathers on the back of the arrow would indicate the speed. Well, over time, we got more and more stations, the map got a little more crowded, and to use less ink and to reduce the clutter on the map, this thing went away. So we were left with just that, indicating, again, southwesterly winds at that station at about 25 miles per hour. And if you take this concept and apply it to the rest of that map, you'll hopefully see one wind regime in one part of the state and another wind regime in another part of the state. And a couple just tiny caveats. A calm wind at the station is just a circle around the station with no stick. So that is a wind near zero. And a 5 mile an hour wind at the station is just depicted by a short little stick like that with a little bit of the longer stick hanging off, just to help you know. So calm wind, 5 mile an hour wind from the southwest, 25 mile an hour wind from the southwest. If the winds were to switch around to the northwest at this station, it would end up looking like that. So that the wind is switched to a 20 mile an hour wind from the northwest. And again, this is at that station, at the end of the tip of the stick there, is what we're going after. Best of luck on your map assignment and on the rest of your week 2 material. If you do have any questions, please post a question on the discussion board, or better yet, send me a message, and I will get back to you within the day or so. Please stay safe if you're out of the country, and for the rest of you, please enjoy this week 2 of our class.